Hello, my people. Hope we're doing well. This video is meant to supplement our discussion in class of 11.8, where we were discussing for the first time power series. We talked about convergence and divergence of numerical infinite series in sections 11.3 to 11.7. So it's kind of a nice segue into power series for this section to be about the mechanics of finding not whether power series, meaning series that have variable terms rather than numerical terms, whether those series are convergent, but where they are convergent. Okay, and to do that, we're going to wind up using the ratio and root test like we discussed in class. But let's cover the bases first. Now, a power series will always have this form, right? It looks like an infinite polynomial because in some sense it kind of is, okay? Now, if x is a variable, then an infinite series of the form, of whatever your coefficients are, and then x squared, x cubed, x to the fourth, x to the n, x to the whatever, is called a power series, okay? That one is centered at 0, because notice that it's just x by itself. It can, however, be centered elsewhere. And so you have the sigma n is equal to 0 to infinity of whatever formula or whatever coefficients they have, and then x minus c to the n. And so you don't have x squared, x cubed. You have x minus c squared, x minus c cubed. And then, of course, x minus c to the n, and on and on and on and on. Now, I sort of cut and pasted this from another textbook. Your textbook has exactly the same thing, except it swaps A's and C's, but the meaning is the same. And that's kind of like some books use n for their infinite series, and some books use k. And we've done tons of examples on the board from those other textbooks that use k rather than n. But like I said, the meaning is the same. Now, power series, as I've told you before, are often used to represent functions. We're not going to concentrate on that part of it, however. In this section, we're just going to talk about convergence and intervals of convergence and a radius of convergence. So the question that we need to be contemplating in this section is, for what values of x does the power series converge? And so let's actually start with a really easy one, okay? One that is very easy to understand. And basically we have x to the n. So it's 1 plus x squared plus x cubed, and on and on and on, plus x to the n, plus, x to whatever, the infinity, right? The question then becomes, where is this? Where is this convergent? Now, as you've noticed, because x is by itself instead of x minus 2 or x plus 5, then it's centered at 0, okay? And here we're going to use the ratio test. Now remember, the ratio test, when we were dealing with numerical, let me go ahead and just write it. N goes to infinity of a n sub 1 over a sub n. And basically it comes out to have some number. Now if that number, it converges if it is less than 1. Okay? So it converges if it's less than 1. If it's greater than 1, it diverges. And if it is 1, then it's inconclusive, okay? We're going to do something very similar here for the power series. And so we have the limit as n approaches infinity of x to the n plus 1 over x to the n. And that actually leaves us with the absolute value of x. Well, the absolute value of x is less than 1. Well, that shouldn't surprise us that that turns into negative 1 to 1. Okay, so basically the absolute value of x has to be less than 1 for it to converge. So therefore x has to be between negative 1 and 1 for it to converge. But remember, if it's actually equal to 1, you can't tell from the ratio test whether at that exact value it's convergent or divergent. So now you need to check the endpoints. So we need to check when x is equal to negative 1. And then we need to check when x is equal to 1, and that will give us a greater idea exactly what the interval is, whether the interval includes these endpoints or whether it doesn't. So we take this negative 1 and we go back up to the original, and it goes n is equal to 0 to infinity of not x to the n, but negative 1 to the n. Well, we know that just like, and we've seen this before, it's just going to bounce back and forth between 1 and negative 1. So it's going to be 1, minus 1, plus 1, minus 1, plus 1, minus 1, plus 1, minus 1. And while it doesn't go off to infinity, it certainly doesn't actually converge to any particular number, and therefore we know that this is divergent. Here, this one becomes even easier because it becomes 1 to the n, and that's 1 plus 1 plus 1 plus 1 plus 1 plus 1 plus 1 all the way out. That is also going to diverge. Therefore, our interval of convergence, okay, is going to be negative 1 to 1. Now, there's also what's known as the radius of convergence, okay, and that is how far away from where it is centered do we find those endpoints. And of course, for our purposes in this one, the radius is that right there. It's 1, okay. And that brings us to the close, and we're ready to go, okay? Now, okay, let's do another example. Now, we have the radius and interval of convergence for the following power series, and it is sigma n is equal to 0 to infinity of n factorial times x to the n. Okay? So it's pretty similar to the previous one, except for all of a sudden we have n factorial in there. So let's go ahead and do the ratio test, and we have the limit as n approaches infinity. We have n plus 1 factorial x to the n plus 1 over n factorial x to the n. Well, that simplifies pretty easily, right? Because n plus 1 factorial is just n plus 1 times n factorial, and x to the n plus 1 is x to the n times x. N factorial x to the n, and we see the fact that those are identical, so they actually cancel out, and what we're left with is the limit as n approaches infinity of n plus 1 times x. Well, n plus 1 is just going to get larger and larger and larger and larger. So basically this goes to infinity. But in order to determine the interval of convergence, this has to be less than 1. So that's kind of curious, okay? Because that right there is not and never true, okay? Okay, what's actually the case is that infinity is, of course, greater than 1. So we have a problem there. What this means is that when you get infinity like this and it is less than 1, okay, the series converges only at its center, okay? And therefore the radius of convergence is 0. So what happens here is we really have three basic scenarios when we are faced with a power series. Okay, if we have something that comes out with a variable expression less than 1, then we need to solve that inequality and determine the interval and the radius. And then we need to check the endpoints for convergence and divergence because those are ambiguous or at least indeterminate from using the ratio or the root test. If you get a numerical answer or an infinite answer, then you have to decide, okay, that means basically that either way, the variable doesn't matter. It's either always true or it's never true. If you come out with a answer that is always true, then you have a interval of convergence of negative infinity to infinity. If you come out with an answer that is never true, then it converges only at the center. And here are the three sort of scenarios. Okay. Series converges only at C, and this, of course, is when you get a false answer from the limit. There exists a real number R such that the series converges absolutely and diverges, okay? That is basically when you find the interval, and here, this is when you get a true answer, something that is always true. The series converges absolutely for all x, negative infinity to infinity. So let's do a bunch more examples to sort of flesh all this out. Okay. Find the radius and interval of convergence for the following power series. Alrighty, so let's go ahead and set up the ratio test again. Most of the time it's going to be ratio. There is going to be an occasional root test, and we'll get to that here in just a moment. We're going to go ahead and convert it to n, since n is our comfort zone. Okay. But again, like I said before, the k's mean the same thing as the n. It's just basically the choice of the textbook author or the textbook editor and publisher. Okay, so this first one right here is this right here, remember, this is your a sub n plus 1, and this is your 1 over a sub n. So you're multiplying by the reciprocal of the a sub n instead of putting it into a complex fraction. It just winds up being a little bit easier to express that way. And of course, the x to the n plus 1 cancels with the x to the n, all but one of the x's, okay? And then these natural logs actually don't cancel, and I'm going to get, let's just go ahead and put x times natural log n over natural log n plus 1. Well, this right here, okay, goes to 1, okay, because the larger that infinity gets, and remember, because natural log sort of flattens out, right? It flattens out, so the previous output of the natural log function is going to be closer and closer to the next output, and therefore as you go along, this whole thing goes to 1, and you're just left with the absolute value of x. And you know that since that is now a variable answer, we need to solve that inequality, and it's really easy. That inequality is negative 1 to 1. But like I've said before, the ratio test is inconclusive when it actually is equal to 1, so we need to go ahead and numerically check those endpoints. So we'll check when x is equal to negative 1, and we'll check when x is equal to 1, okay? So when x is equal to negative 1, we get negative 1 to the n over natural log n. Well, that's obviously going to be an alternating series. And the alternating series just asks you to do two things. Is each successive term less than the previous one in terms of its absolute value? And as n goes to infinity, does your a sub n go to 0? And the answer is yes. So by alternating series, this converges. When, of course, you get over here and you get 1 to the n over natural log n, you recognize that this is going to diverge by comparison to a p series, right? Because 1 over n, as the harmonic series, doesn't converge, it diverges, and this is going to be even less aggressive than that. So your interval winds up being negative 1 inclusive, 1 non-inclusive. Your radius, of course, is just going to be 1. Now, let's go ahead and do another one. I like this one because now we have our first example of one that is not centered at 0. This one, of course, is centered at 2 because of your x minus 2 right here. We can go ahead and use k this time. Let's do the limit as k approaches infinity, and your a sub k plus 1 is k plus 1, x minus 2 to the k plus 1, 3 to the k plus 1, and of course this is going to be 3 to the k, k, and x minus 2 to the k. Now the simplification process, again, ought to be pretty simple. All of this cancels with all but one of those. All of this cancels with all but one of those. And when I rewrite it, I can get the limit as k approaches infinity of k plus 1 over k times x minus 2 over 3. And the reason that I do that is this limit is with respect to k. So I basically, this right here, even though it has an x and is a variable expression in terms of other spheres, with respect to the limit, it's a constant because it is not entertaining the variable that the limit is entertaining. Okay, and entertaining is probably not the right word, but you get what I'm saying. This right here goes to 1 as k goes to infinity. So what you now get is x minus 2 over 3 is less than 1. Well, when does that happen? Well, the great thing about that 3 is this gives us also our first example of one where the radius of convergence is no longer 3. Because if the center is at 2, x minus 2 is less than 3, and it turns into that kind of three-part inequality, at which point we have negative 1, x, and 5, and now we know that our radius of convergence is 3, not 1 anymore. All we need now is to determine our interval. And in order to finalize our determination of that interval, I need to go ahead and entertain the endpoints. So when x is equal to negative 1 and when x is equal to 5. When x is equal to negative 1, I'm going to get k is equal to 0 to infinity, k. And if I plug in negative 1, this becomes negative 3 to the k over 3 to the k. Well, you can actually pull the negative 3 to the k apart into negative 1 to the k and 3 to the k, and this can be actually rewritten as k, negative 1 to the k, 3 to the k over 3 to the k. Those, of course, cancel out, and basically k gets bigger and bigger and just flips back and forth between positive and negative. This, ladies and gentlemen, is definitely going to diverge. All right. Now this other one, when x is equal to 5, get k is equal to 0 to infinity, k, and 5 minus 2 is going to be 3 to the k over 3 to the k. This takes a little less work. Those cancel out pretty easily. You see, however, that this is just going to be successive values of k added together. That definitely is divergent. And my interval is non-inclusive on both of its endpoints. Okay. Now, let's go ahead and let's do, I think we'll go ahead and call this video, bring this video to a close, and I'll start with the next example on the next video, because I don't want any one video to be too long. But again, if you have any questions, please do shoot me an email. Bye.